Sometimes you might hear people talk about the generative process specification for a probability distribution. And this is basically a handy convention for specifying a probability distribution in a more compact way. And it's made more compact because you leave out certain conditional independence properties from the specification. And when you use this convention, those conditional independence properties are implicitly implied. So it's called a generative. People refer to this as a generative process specification, but there's nothing that's necessarily generative about a model that you specify in this way. It can be applied to other types of models as well, but it's maybe most applicable to generative types of models. So what is it? What is this? What is this thing? So instead of giving you a formal definition, let me just give you a little example. So this will be the generative process for a particular distribution. So let's see. Let's say we've got x1, x2 are random variables, and let's say maybe they're Bernoulli with probability 1/2 and independent. So I'm giving you the generative process specification for a particular distribution. So this would be x1 and x2. And then let's say x3 is a random variable. And let's give it some distribution that depends on x1 and x2. So maybe it's normal, say. Maybe its mean is like, say, x1 plus x2, something like that. And variance, I guess, I don't know, sigma squared, some constant sigma squared. And let's do some more. Let's say x4 has so x4, let's give it some distribution, and we're going to give it a distribution that depends on the random variables that we previously defined. So let's say that x4, maybe it's also normal, and maybe it is depends on, maybe its mean is, I don't know, let's say maybe it's like a, some constant a times x2 plus some constant b, something like that. Maybe variance 1. So at each step here, right, the distribution that I'm defining for x3, for example, depended only on the previously defined random variables. And then x5, let's do one more. Let's say x5 is equal to 1 if x4 is greater or equal to 0. I'm just making stuff up. This is just totally arbitrary. The important thing is that at each step, the random variable, the distribution, depends only on the previously defined random variables. Okay, so this would be the generative process specification for a particular distribution. And the convention, is the following. So the convention is that when you say this, you mean that these random variables have that the joint distribution, like if x is the vector of all these, that x, that's a funny looking x, that x respects the following graph. So the graph is the graph that it respects follows the sort of order of these definitions. So we had x1 and x2, and they were independent. So we draw them this way. And then x3 depends on the definition of its distribution dependent on x1 and x2. So we would put x3, we would put an arrow from x1 to x3 and from x2 to x3. And then x4, we would have x4, and it depended on x2. And x5, the definition for its distribution depended only on x4. So the convention is that x respects this graph. And in other words, that this graph, since x respects this graph, that implies that x has certain conditional independence properties. And those conditional independence properties are not necessarily implied by these statements here. So for example, so x3, this graph implies that x3 and x4 are conditionally independent given x2. That might not be immediately obvious at this point, but a little later on we're going to look at the conditional independence properties, some shortcuts for evaluating and understanding what the conditional independence properties implied by a graphical model are. And so maybe it'll be a little more obvious later on why x3 and x4 are conditionally independent given x2 under this graph. But it's possible that these statements could each individually be true, and if we weren't following this convention, that x3 that might not hold. For example, so let's see, I won't be able to probably make this explicit, but here the marginal distribution or the conditional distribution, let's say, so under the marginal distribution on x1, x2, and x3, these statements could hold. x1 and x2 could be Bernoulli under that marginal, and x3, condition on x1 and x2 might have the conditional distribution where you set those equal to their values. And also, at the same time, it might be that x2, the marginal distribution on x2 and x4, satisfied this property and this, but that x3 and x4 had some other dependency between them. So it's possible that these statements could hold, and x3 and x4 could still be conditionally dependent given x2. It's possible for that to happen. Might be simpler examples with coin flips might be easier to see. Like if you had a coin flip, like, well, I won't do that explicitly now. So let me just write down just to remind you what this means. X respects this graph. That means that your joint distribution x1 through x5 equals probability of x1 times the probability of x2 times the probability of x3 given x1 and x2, that's this part, times the probability of x4 given x2 times the probability of x5 given x4. So the convention is that when you're using this convention and you say this, that you mean that the distribution satisfies this property, that it factors in this way. Okay, so I just wanted to give you tell you what this means if you hear that. And also I wanted to tell you this because this is a really nice way to sort of think about a probability distribution, right? If you have a distribution and you have a graphical model like this, you could give it a generative process specification in this way. You specify x1 and x2, and then x3 depends on those, and so on and so forth. And it's a very nice way to sort of intuitively envision or visualize the joint distribution. You can sort of just intuitively, you can imagine drawing samples, and actually, so that's a good way to draw samples from a distribution like this, is to draw samples of x1 and x2, flip a couple coins, and then you take their outcome, you add them together, and then you draw a normal random variable with this mean for x3, and then you would draw a normal random variable for x4, and you would make it conditionally independent. So when you drew x4, that draw would only depend on the value of x2, but that might not necessarily hold. So I keep emphasizing that this is a convention. So you would draw that independently of everything else, just depending on x2, and then you would set x5 equal to the appropriate value, and that would give you a way to sample from that joint distribution, a very sort of natural way. So another thing, just write nice for sampling and visualization. Okay, so I just wanted to tell you about that little sort of handy convention of the generative process specification.